Hello friends, welcome to our channel Knowledge Amplifier. So in this particular video we are going to explore the concept of Bloom filter, and we will also observe how this filter basically optimize the query performance in our Delta Lake tables. Okay, right? So you might have already encountered this concept while exploring data structure and algorithm course during your BTech, but here I am going to give you a quick idea or theoretical understanding of this filter, so that you will have the intuition that how this filter is working in the backend. So a Bloom filter is a space efficient data structure that lets you quickly check whether or not an item is there in a set. So let's try to understand this particular definition with one example. That is, suppose you are having a website, okay? And in that website, any new user, when they try to sign up, they need to provide a unique user ID. Now suppose you have to design this particular system. How you can do in one way is basically, whenever any user try to provide some user ID, you go to the backend database. Okay, here your backend database is there. There in that specific table you can search, that is select count star from the table name where user ID equal to the user ID provided by the new user, and if the count you are getting 1, that means that user ID is already used and you may return this user ID is already utilized. You might need to give some other user ID for sign up purpose. So that can be a pretty simple or straightforward architecture. But suppose think like this, a lot of users are trying to sign up, and if for all of the users if you need to go back continuously to the backend system, execute the query, then it might be little bit inefficient approach. Compared to that, there is an optimized approach developed, and that is basically Bloom filter. So let me erase some part and I will try to explain you how that works. Okay, so here I will erase this part. So here is our architecture, that user is there who try to sign up in our website, and our backend DB is there. Whenever user will provide some user ID in the web portal, here first what it will do, it will go to a specific data structure which is called Bloom filter, and there it will have a check whether this user ID existing or not. Now what kind of outcome Bloom filter basically gives, that I have highlighted here, that Bloom filter either confirm it's definitely not there, or it return it might be there. For not there case, it is 100% sure. But when it is a positive case, that is the user ID is already used, it is not 100% sure. Okay, it says it might be used. So now this output can help in optimizing this system overall. If you see how, that is, suppose a user is putting some user ID and it will go to Bloom filter. Bloom filter can quickly return us whether it's definitely there or not, or it might be there. If it is returning it's definitely not there, then there is no problem. User can continue with that user ID and then they can make an entry in backend database. But if Bloom filter is returning it might be there, that time what will happen? That time this backend system need to go to this backend database for 100% confirmation that whether this user ID is really used or not. Correct? So due to application of this Bloom filter, what is happening, if you observe, that when Bloom filter is returning it's definitely not there. That means for some cases it is quickly returning this user ID is definitely not at all utilized, right? In those specific cases, the backend system no need to apply any query in the backend DB. That way some sort of load we have reduced in the backend database, and that's how it is optimized. And that's how the Bloom filter helps in improving the efficiency of our overall system. So what it does, it basically return it's definitely not there or it might be there. Okay, kind of a search engine you can consider, which is space efficient, and it is a data structure which let us quickly check. Okay, it is a very vital factor that it is very fast. Okay, it helps us quickly checking whether anything is definitely not there or it might be there. That's all, right? And this concept not only in this backend use case, but it helps us in optimizing the query performance in Delta Lake as well. We will try to understand how, but before that let us try to understand how this Bloom filter is working, how it is telling very quickly that whether anything might be available in a set or if it is definitely not there in that set, that let us try to understand now. Okay, so I'll clear all this. So now to understand the working principle behind this popular Bloom filter, let us try to understand the data structure in detail. Okay, here I have written some handwritten notes. Try to understand from this what is happening. For Bloom filter data structure, we have some sort of bit array. Okay, so here let me write bit array. So for this example, we have considered our Bloom filter size is 8-bit array. Okay, what we are using. Now initially in this bit array, all bits are set to 0. If it is set to 0, that means it's definitely not there. Now because we are considering the fresh example, so we will start with insert phase. Obviously initially some data should be inserted, and then only we can apply some search or check whether anything is available in the existing set or not, right? So first we will understand the insert phase, and then we will check how searching is working in a faster manner with this bit array. So suppose user is trying to insert one string called chocolate. How this chocolate will have an entry in this Bloom filter is basically all Bloom filter use some hash function in the backend. So first we will have hash of chocolate. We'll get some long integer type data, right? And because our bit array is of size 8, so let's consider a simple hashing algorithm here, that whatever value we will be getting after converting this string to long integer using hashing, we will divide the data by 8. Okay, because our bit array is having length 8, and after dividing by 8, whatever remainder is there, in that place we will mark or set the value 1 from 0 to indicate that chocolate is used. Okay, so first step what I am telling you, that whenever suppose we are trying to make an entry of chocolate, first we'll apply hashing of chocolate, we'll get some long integer, and because our Bloom filter is having size 8, so we'll divide by 8, and suppose after the division the remainder we are getting 3. Okay, so if you observe here, for the index 3, here we have made the bit set to 1, right? So this is how the insert phase for chocolate is working. Suppose next we are having another insert, for example red velvet. We'll apply the same algorithm. First we'll get the integer representation using hash value of red velvet, and then because our Bloom filter is of size 8, so we'll divide by 8. Whatever remainder we'll be getting, suppose that is 6, we will go to this index 6 and we will set the bit to 1 from 0. Okay, so this is our insert phase in Bloom filter. And I hope obviously you are getting this, that because we are dividing by 8, so always remainder possibility can be 0 to 7. That is pretty much understandable. Similarly, if you divide something by 3, the possible remainders only can be 0, 1 and 2. If you divide anything by 5, possible remainders are 0, 1, 2, 3 and 4. Like that way how it works. Correct? So this is how our Bloom filter is inserting. I hope up to this it is pretty much simple. So this is how insert phase works in Bloom filter, that whatever string we want to make an entry, we will first get its integer representation, and then we will divide by the length of the Bloom filter, and whatever remainder value is there, that position's bit will be setting to 1. As simple as that. Okay, here I am explaining with a very simple algorithm, but in the backend very complex algorithm works. You don't need to consider that this is what actually works in the backend, but to give you an intuition of working principle of Bloom filter, I have taken this simple algorithm. Okay, now suppose insert phase is over, and now I want to query whether this chocolate string is available or not in our Bloom filter. Now let us try to understand how Bloom filter quickly can tell us whether this string is surely not available in the data structure or it might be available. How it detect, let us try to understand. Okay, so user will query whether chocolate is there or not. What Bloom filter will do, it will apply the same algorithm. First, it will get its integer representation using hashing. It will divide by 8. Whatever remainder it will be getting, suppose 3 it is getting. Earlier also it got 3 due to insert phase. Now in search phase also it will be getting 3 only, because hash value of chocolate will not get changed if we are applying same hashing algorithm. And when you are dividing by 8, we will always get the same remainder. Correct? Now what we'll do, we will check at this index whether the bit is set or not. If you observe here, this bit is set, so we can say that chocolate might be there. Okay, very important, it is not saying that it is there. It is saying it might be there. Why it is saying so? Suppose here I am having a string A and I have applied hashing, and after hashing I am getting the integer as 1, 2, 3. Now it is possible that in the whole world there is another string b, where if I apply same hashing algorithm, we might get the same integer 1, 2, 3. So in this Bloom filter algorithm, if a bit is set, then we can only say that chocolate might be used, but we cannot say for sure chocolate is used, because in that specific position the bit is set to 1. That can be for the chocolate string, or that can be for some other string which is having same hash value as of our chocolate data, right? So that's why Bloom filter is returning it might be there. Okay, very important. Now let's go to the next case in our search process. So suppose this time user is querying this one, apple. So as a first step, what we will do in Bloom filter, we will apply same hashing algorithm whatever we have used in insert phase, and hash of apple whatever we will get, that will divide by 8, and remainder suppose we are getting 2. Okay, now we will go in our Bloom filter and we'll check whether in the index 2 the bit is set or not. Now the bit is 0 here. That means definitely the apple is not there. If the bit is set to 1, that means there is a possibility that that string is already used, because it might happen that due to hash value of that string and then divide by 8, the remainder whatever we are getting based on that, the specific position is filled, or maybe for some other string with same hash value has filled that position. But suppose if a location is having 0, that means no such hash value was used which is having same outcome as of apple. That means apple itself is not at all used. So that's why Bloom filter in this case clearly returning for sure it is not used in this set, right? So this is also correct case. I hope you are getting this up to this pretty much simple, that Bloom filter is returning maybe it is there or for sure it is not there. Then another example, if we consider query equal to carrot we are applying. Now hash of carrot we have applied, and after dividing by 8, suppose remainder we are getting 6. Now when it will go to index 6, it will get the bit is set, right? So that time it can say the carrot might be used, but actually we have seen earlier, right, that carrot is not used. The index position 6 was set due to another string, and that is red velvet here. In this algorithm, red velvet's output was also 6, and here carrot's output is also giving 6 only. It is happening because there is a possibility that whatever hash function we are applying in that process, integer value of carrot and red velvet are same. That's why after applying this algorithm, we are getting same outcome for both of these strings. So that's why it is returning it might be there, and this is a false positive case. Although carrot is actually not there in our set, but it is returning it might be there. So this time when it is saying it might be there, we might need to go to the actual backend database. In our example, what I was talking with respect to website sign up, in that specific scenario, whenever Bloom filter return it might be there, that time we can go to database and apply the select query, not a problem. But at least for some cases, Bloom filter is quickly giving for sure it is not there, right? So that way backend database query part for many scenarios can be reduced. It no need to go to the backend database. From that Bloom filter itself, it will get the idea for sure this user ID is not used. So this is how in the backend Bloom filter is working, and that's what I have highlighted here as well. That note, the false positive is not a bug. It is a trade-off we have made to keep our checks faster. That is the overall sense of Bloom filter, that it helps us in quickly detecting whether a string is definitely not there in a set or not, or it might be there in a set or not. So this is a generic intuition of Bloom filter. Now obviously very much complex algorithm nowadays is used in the backend with much optimized version, so it works in much better way in real world scenarios as well. But I hope with this simple note, the intuition of Bloom filter, how it is working in the backend is clear to you. Cool. So in our next section, we will be exploring how this filter helps in optimizing search operation in our Delta Lake in a faster manner. Stay tuned. Now in this specific section, we will be exploring, or we will try to get some intuition on how Bloom filter basically used in Delta Lake and how it optimizes the search query. Okay, so suppose here we are having our Delta Lake, and here we are having underscore delta underscore log folder, and then outside that we are having lot of Parquet files. So Parquet 1, Parquet 2, Parquet 3, and so on. Okay, And now suppose we are having a specific column in this delta table on which we want to apply Bloom filter search. Okay, and that particular column is having some values like A, B, C, D, E, maybe some kind of text column we can consider. Now let us try to understand in this specific context how Bloom filter is basically implemented in Delta Lake. So what Delta Lake does, for each Parquet file, it basically generates the bit array what we have earlier discussed while covering Bloom filter. That is, here when we have discussed the Bloom filter concept, you understood that the fundamental data structure in the Bloom filter is available kind of a bit array. Like earlier we have considered an 8-bit array, 0 to 7, that index positions are there, and that index position you can consider kind of a key in our dictionary, and in the value part initially all will be 0. If any value we try to ingest, the value part we convert from 0 to 1 for that specific index key. Kind of in a sense, Bloom filter is nothing but a dictionary data structure where the key are basically indexes of our bit array and the value part is basically denoting 0 or 1. 1 means the data might be there, 0 means for sure the data is not there. That kind of intuition you can think of, right? Now here in Delta Lake what it does, it basically create bit array or that dictionary for each Parquet file. Okay, so for this Parquet file we'll be having one bit array which has implemented Bloom filter, and then same for our Parquet 2 and same for our Parquet 3. Okay, let's consider for the time being that it is having size 5. Okay, so here I'll be doing that. So these are basically extra data whatever Delta Lake store to implement Bloom filter, because I hope you were getting this, that this mapping in our S3 Data Lake somewhere it need to store so that it can take help of this specific data structure for efficient query purpose, right? Now what Delta Lake does, suppose here we are having the column, maybe column name we can provide call1, and on top of this call1 we are applying Bloom filter, right? So that time Delta Lake will go to each Parquet file, and for this specific column 1, it will populate the Bloom filter. So initially for all these data points, it will be having 0 in the value part for our Bloom filter. But suppose if you consider Parquet 1, in this Parquet 1 for this call 1, we are having only two distinct values A and B. Okay, and suppose hash value of A is getting mapped to 1 after dividing by 5, the remainder whatever we are getting is 1. And for the column 1 value B, after getting the hash and dividing by 5, suppose the remainder we are getting 3. Okay, so for this Parquet file in the Bloom filter, because A and B only these two distinct data points are available, so in the index 1 it will be setting the bit to 1, and for the data point B in the index 3 it will be setting the value to 1, and rest it will be keeping 0. As simple as that. And let's consider Parquet 2 now. Suppose in Parquet 2, we are having C and E, these two unique values for the column 1. And suppose after applying hashing and then dividing by the value 5, the outcome for C is 0 and for E we are getting 2. So what will happen for the Parquet 2 in the Bloom filter, because we are getting 0 because of C data point, this position bit will be set to 1, and for E data point, this position bit will be set to 1. And rest will be 0 as a default. For Parquet 3, let's consider in the column 1, we are having data point A and D. Now, if we apply hashing on A and divide by 5, we will get outcome as 1, just the same whatever we have got in Parquet 1 file, right? So due to that, in this 1 index, it will be setting the bit to 1. And suppose for D data point, if we apply hashing and divide by 5, suppose we are getting the remainder 4. Okay, so that time, because D data point is available in Parquet 3, this value will set to 1 and rest will be by default 0. So this is how this Bloom filter data for our Parquet file will be created, right? Which will be associated with each Parquet file, and I hope you are getting this intuitively, how this Bloom filter data is getting generated, because already in our previous section we have covered this concept in detail, right? And now suppose I am applying a select query, select star from delta table 1 where call 1 in C, D. Okay, right? So this is a common SQL query. Suppose we are applying on our delta lake. And let's consider Bloom filter is not configured in our Delta Lake. Then what would have happened? So when you have explored Delta Lake in detail in our previous video, that time we have seen Delta Lake stores statistics in the metadata information or in Delta log. So in the statistics for each column, what is the minimum value and what is the maximum value, that generally is available, and based on which sometime Delta Lake apply data skipping concept. For example, I am searching, suppose call2 value should be 9, okay, and for a particular file in the metadata column you can see for that specific parquet file call2 minimum value is 10 and maximum value is 15. So if this information you are having with respect to statistical data, then that parquet file you will not even query or scan to get the data for call2 equal to 9, because call2 9 is lesser than the minimum data whatever available in that parquet file. So you will not scan that parquet file, and this is the general concept of data skipping operation what we have explored in detail while discussing the jet order filtering in the Delta Lake optimization. But this concept you cannot apply on string data, because these are string, so statistical mean value max value may not work in a very good manner, and that's where Bloom filter comes into picture to optimize the search query with respect to string data. Now in this table we have applied Bloom filter and we have already this data handy. As a lookup we can use this data, right? Now when I am querying select star from table where call1 in C and D, instead of directly going through each parquet file, what Delta Lake will do, it will go to the Bloom filter data first, okay, and for C it will apply the hashing and then divide by 5 suppose for example, and it will get that for C the representing data is 0, what we have got earlier also, and for D the representing data is 4, what we got here. So it will try to find out for what all parquet files in index 0 and index 4 the bit is set to 1. That way it will be optimized and can skip other unnecessary parquet files. So when it will scan the Bloom filter for index position 0, the data is set to this specific parquet file, so it will consider parquet 2 for scanning, and index 4 is set here. So for data D, it will scan the parquet 3 also, right? And it will skip the parquet 1, because for parquet 1, neither in index 0 nor in index 4, the bits are set to 1. That means for sure, column 1 in this parquet 1 file is not having value C or D. C or D related data is available only in these two parquet file. So that way our Delta Lake now will scan only in parquet 2 and parquet 3, and it will skip the parquet 1 file. So this is how data skipping operation is working in Delta Lake with help of Bloom filter. I hope the intuition is clear to you that when you apply Bloom filter on top of Delta Lake, then along with Delta log directory where transactional logs are stored, along with actual data files, it also stored Bloom filter data for each parquet file. Whatever Bloom filter array will be created, that it will be storing separately, and that will help us in performing data skipping operation. I hope this intuition you got it. So now we will start the practical implementation of Bloom filter in Delta Lake with Databricks. So as I already told you, that a Bloom filter index is a space efficient data structure that enables data skipping on chosen columns, particularly for fields containing arbitrary text, right? This point is very vital. Sometimes we might have lot of numeric columns, and if we are applying filter on numeric column, then statistics based data skipping works very well. Even you can opt for data partitioning if the column is having low cardinality. But suppose you are having a column on top of which you apply frequent filter condition or where clause, and that column is having very high cardinality. So as a result, you cannot use that as partition column as well. And suppose that is a string column. Now suppose in that string column, for example, email address, you are having abc@gmail.com. to 𝒁𝒆𝒓𝒐@gmail.com. So in this case, A to Z, all data points are available. So even if you consider the minimum and maximum value with respect to statistics, all data points in alphabet it is covering. Suppose you are trying to search 𝒉𝒐𝒐d@gmail.com, and if your all files are having some email address starting from A and another email address starting with Z, then there is no advantage of data skipping you will be getting, because if you sort lexicographically, BCD will be always falling within this range, right? So sometimes data skipping operation also might not be working with only statistical analytics based on mixed man value range. That time this Bloom filter helps a lot, which I covered in my previous video as well. And now here is a catch, very important. Whenever you try to apply Bloom filter on any delta lake table, the catch is that you want to have a reasonable idea of the number of distinct values that need to be indexed. So what I'm trying to say, when you will try to apply Bloom filter on a specific column, before that you should have some sort of approximately correct idea that how many distinct values are possible in this specific column. And if you ask why, that explanation is pretty much intuitive based on the working principle of Bloom filter. So just let's have a quick recall on the first section what we have discussed related to Bloom filter working principle. So in the backend, as I told you, that Bloom filter implement a bit array or a dictionary, where the dictionary will have this kind of structure. If you consider after the insertion of chocolate, how the Bloom filter will look like: 0 index 0, 1 index 0, 2 index 0, 3 index 1, 4 index 0, 5 index 0, 6 index 0, and 7 index 0. So this kind of dictionary data basically our Bloom filter store, where these values part are basically bit array, whatever we are considering, and the key part are basically this index position of Bloom filter, right? Based on this algorithm, let us try to understand the importance of the size of the bit array. Okay, suppose you are having a table where on a particular column on which you want to apply Bloom filter is having data varying from 0 to 20,000, and you have only a small bit array of length 4, 0, 1, 2, 3, only 4 index it can tackle. Now for example, if you consider this same algorithm, first you take hash value and get the integer representation, and then you divide by 4, whatever remainder is there, based on that you will set certain bit index to 1, right? That algorithm if you consider, because our data point is very huge and our size of the array is very small, then there is a very high possibility that very quickly all these zeros will be converted to 1 in this array. That is because the array size is very small, so all the bit locations will be set to 1 very quickly depending on this algorithm. And once all the bits are set to 1 in our Bloom filter, then this Bloom filter will not at all help us in query optimization, because whatever you will try to find for all index position, it will return value 1, and 1 means it might be there. So that time you need to go to the actual Parquet files in the backend for each Delta Lake files and apply where clause to find out whether it is really there or not. So I hope from this simple example you are getting the idea that Parquet file data skipping will not work well if the range of your data or distinct values in your column is very high and you are considering the bit array for Bloom filter very small. So that's what I have tried to write here in this Databricks notebook, that you should have a reasonable idea of the number of distinct values that need to be indexed. Otherwise, there will be huge collision if the number is too small, as I told you, or if suppose you have only 3 distinct data points 0, 2 and 3, let's consider in a column, and you have considered a bit array of 10 length, for example. So based on any hashing algorithm, when you will try to map this distinct data point to this bit array, only 3 bits will be set, but rest will be empty. So that is unnecessary wastage of storage. So with respect to distinct data points available in your Bloom filter, the bit array size should be controlled. It neither should be very high with respect to distinct data points, nor it should be very small with respect to distinct data points, right? That's what I have tried to highlight here. This is a very vital point when you will try to apply Bloom filter on a specific column for query optimization. Now let's go through the code base. Here as a first step, what I am doing, I am mounting one S3 location with our Databricks kind of Snowflake external stage creation you can consider, which is having the name /mnt/Databricks external stage Bloom. Okay, so this cell I have already executed earlier. So if I execute it again, first it will ask to attach a cluster. So I will start attach and run. So if you go here here you will see that the cluster is getting launched. Once it will be launched, this cell will be executed. Till then it is showing waiting state because our cluster is still spinning up. Once the cluster will be in running state, this cell will be executed, but the expectation is this particular code base should fail because already we have created this external stage. We have mounted the path. So again it will not able to mount it. But just to show you the demo, I am executing this cell again. So here you can see this cell execution is complete and it is throwing an error because directory already mounted. That is fine. So here I have already created this directory within our S3 location, where as of now if you see it is an empty directory. Right? Now here what we'll do, we will basically first drop the table if it is already existing, Bloom filter demo, and here you can see the cell is getting executed. Okay, right? We got the output. Now here what we are doing, we are basically creating a external table pointing to this external stage, whatever we have created, right? Bloom filter demo. If you check this directory, this is the same one which is available here. So here what I will do, I'll execute this cell. Okay, done. Now I want to show you how Bloom filter optimizes the query execution. So for that reason, I should have two identical columns. On one column, I will apply Bloom filter and apply query clause to filter some data. And in another identical column, I will apply the same filter clause but without Bloom filter. And I will show you that when we are applying Bloom filter, then it is having advantage, right? That is what our ultimate goal, to get intuition of working of Bloom filter and the data skipping concept related to Delta Lake, whatever we have covered in our previous video. So for that purpose, here I am creating two columns, key with Bloom and key without Bloom. Okay, right? Now on this key with Bloom, on this column, I'll be applying Bloom filter. So this is the syntax to create Bloom filter on a specific column. Create Bloom filter index on this particular table, and then we have to mention on what all columns we need to apply Bloom filter. So key with Bloom, and then in options we need to pass two arguments, and they are very important. Number one is, as I already told you, that whenever you try to apply Bloom filter on a specific column, you should have a sense of possible number of distinct values available in that column, right? So that you can configure in num items, okay, that I have given. And another property is there in Bloom filter, that is FPP. FPP stands for false positive probability. That is basically, we have already explored while discussing the theory of Bloom filter, that Bloom filter sometimes give false positive response. For example, when we tried to query carrot using this algorithm, it returned 6. In the index 6, the bit is set to 1. And that's why Bloom filter is returning that carrot might be there. But actually carrot is not there in our data set. The index position 6 became 1 due to this red velvet, this data point. So Bloom filter by default have these false positive scenarios. Now in advanced algorithm, whatever work behind Bloom filter nowadays, that require that how much false positive probability you can allow for your use case. Obviously, if the false positive probability is very high, then we can say accuracy of Bloom filter is less, because most of the time it will return false positive that data is not available, but still it will respond that data might be available. And if the false positive probability is very less, that time we can say that Bloom filter accuracy is very high, that reverse relationship is available, right? And I hope you are getting this intuitively, that if we are keeping false positive probability very less, that means Bloom filter need to work in a optimized manner, more complex algorithm or more bigger bit array it might be using in the backend. So obviously it might have little performance hit. That's what I have written here, that this false positive probability number sets a limit on what rate of false positive is acceptable during reads. A lower value increases the Bloom filter accuracy but takes little bit of performance hit. This is because the false positive probability value determines how many bits required for each element to be stored. So in short, we can say that false positive probability obviously impact the size of our Bloom filter, bit array, etc. also. So if we decrease the false positive probability, that means increasing the accuracy. That means overall we need to increase the size of the Bloom filter index itself. That is, the dictionary size or the bit array size also has to be increased. So this note I hope you understood intuitively pretty much well. Now without any further delay, what we'll do, we'll create the Bloom filter. Okay, but before that I want to show you what happened in our Delta Lake. Initially it was empty. If we refresh now, Delta log folder is created, but there is no data file, because till now we just created the table. We have not inserted any data, right? Now if we go to this transactional log, here our JSON data is available. If you download, here you will see that it will have the information that the table is created, right? So I'll just download and show you. So here you can see in the operation it is written create or replace table. Perfect. It is till now pretty much understandable whatever we have encountered earlier. Now when I will create the Bloom filter, as I told you that Bloom filter indexes for each Parquet file it need to store in Delta Lake, that it should show somewhere. So if we refresh now, there is no new folder got created, but if you go within Delta log, here you will see that one more JSON is created, and this transaction is basically capturing that Bloom filter is implemented on the column. So let me open that, and here in the operation you can see create Bloom filter index. So Bloom filter index is created, right? And in what all columns it is created, that also it is showing, that is key with Bloom. That is perfectly fine, intuitive also. Now we will try to insert some data in our table. So this is the query to generate the data which will be required for experimentation purpose with datagen as select. First, for record ID column, I am taking help of monotonically increasing ID function from Spark SQL to generate random numbers. And now I should have identical data in key with Bloom and key without Bloom in these two columns. So that way in this key with Bloom column, I will apply Bloom filter, and I will be keeping key without Bloom as it is. And while applying same filter condition, we will see how Bloom filter is optimizing the performance when we will apply filter on this column, right? So to generate identical data, what I am doing, whatever record ID is getting generated, for that hash value I am taking. So same function I have applied on both the columns. From range and 0 to 1 lakh I am going with increment of 1, and this 100 is basically indicating that 100 data files should be created in our Delta Lake. So approximately 1000 rows per Parquet file should be available, because 1 lakh divided by 100 is becoming 1000, right? And that data after generating, I am inserting the data. So generally what should happen, that here our Delta log is there, where as of now one JSON created for table creation and one created for Bloom filter, right? Now outside this particular Delta log folder, our Parquet data should be available. But when I will execute this query, one more thing we should observe, that one new directory should be created where for each Parquet file, the bit array or that dictionary, that Bloom filter lookup should be also created. So I will run this one, and here our Spark job is running, and it is done. Here you can see it has inserted 1 lakh rows. Let's go back to our Delta Lake. If we refresh, here you will see that Parquet files are there. How many Parquet files will be created? 100 Parquet files. So if you just select all, and if you scroll below, here there are two folders. If you deselect these two, the count you will see 100. That means calculation wise it is also working fine. 1 lakh rows, and it is divided into 100 files. That's how here it is getting generated. Delta log, which is basically storing our transactional log data, that itself earlier also available. New point is delta underscore index. This is a new location overall created, and I hope you are getting this. This is basically storing the Bloom filter index lookup for each Parquet file. For example, if you consider this Parquet file, and if you go to delta index, here if you search, here you will see that for this Parquet file, this is the Bloom filter index. You can download this data, and I can take help of any online Parquet viewer, and here I can upload the data. So data is uploaded, and I will open Notepad++ also for visualization. So here I have opened a new Notepad cell, and then here you will see that our data looks like this. And I hope from this data itself you are getting the idea that ideally Bloom filter should look like this only. That is key with Bloom, on top of which column we have applied Bloom filter, and then the actual data structure should be a dictionary, because already we have explored this, that dictionary should be created where index positions are key and value should be 0 or 1. 1 means it might be there, 0 means it is not there, right? So here if you see key with Bloom column is mentioned, that is indicating on this column we have applied Bloom filter, and then our dictionary is available. Dictionary key, if you observe 0, 1, then 2, then 3, then 4, 5, like that way monotonically it is keep on increasing. In the value part, if you see, value part is only taking position 0 or it is taking position 1. In some places it is taking 1. So how these 0 or 1 are coming? It is coming from the Bloom filter algorithm. That is, first what it is doing, it is going to key with column which is available in our actual Parquet data. On top of that, it is applying some hashing algorithm, and then it is performing some sort of division operation maybe, and whatever remainder is there, based on that it is setting some specific index position, bit set operation it is doing, and it is converting to 1. Now these data will help us in applying filter condition in optimized manner or skipping some specific data files, and that I will show you now. So Bloom filter data we have observed. Now if you try to inspect the data in your table, here you will see that key with column and key without column is having identical data, and record ID is monotonically increasing ID. That is fine. Now what I will do, I will apply some where clause. Same condition I will apply in both key with Bloom and key without Bloom, both cases. So first let's apply on key without Bloom. So I will run this cell. So here it has written the data. Now here in Databricks, the beauty is you can always click on the job view and inspect what is happening internally. So here you can go to associated SQL query. So that way it will be showing you the actual SQL query. And if you scroll below, as a first step, what it is doing, it is scanning the Parquet files, whatever available in our Delta Lake. And it has scanned whole 1 lakh data. You can see here, right, that from this layer to the next layer, it is giving output of 1 lakh rows. Because this time we are applying the filter on key without Bloom. That means Bloom filter is not implemented. So there is no data skipping operation working, and even statistical data it is not able to take help because this data is very much complex string data. So data skipping is not working well with respect to statistics based min max value consideration, right? So no optimization is working. Now what we will do, we'll apply the same code. Here if you see, same filter I am going to apply, but this time with key with Bloom, and I will run this. So here also it has taken almost same time, 1 second. Here also 1 second it took, but we will observe what changes it is doing in the job view tab. In the associate SQL query, if you go and if you scroll below, here you see the beauty. It scanned the Parquet file, but from this layer to the next layer it returned only 1000 rows. That means rest rows, rest Parquet files, it has not even opted for scanning based on this specific Bloom filter lookup. Okay, and how it is working, I have already told you in my previous video that first what it is doing, it is taking all these values whatever we have applied on this filter class, it is applying that same hash algorithm whatever it has applied earlier, and then maybe it is doing some division operation, something like that, and getting the outcome for each of these value. Like maybe for this particular data the output can be 0, for example, let's consider, by applying the algorithm. And now it will go to the Bloom filter lookup file and it will check for that particular file whether in 0 index the bit is set or not. If the bit is not set here, that means for sure this particular data point is not available in that respective Parquet file. So that means that particular Parquet file data read operation can be skipped like that way. Same operation it is doing for all these 3 conditions whatever we have applied in in clause, right? So this is how overall Bloom filter index is optimizing the query performance. Maybe this time with this smaller volume of data we have not inspected that the query ran faster, but intuitively we understood clearly that it is scanning lesser volume of data, and that is the beauty of Bloom filter indexing application on Delta Lake, that it optimizes the filter query. So I'll be sharing this notebook in the description box. Try to perform this experiment, try to inspect the job tab, how it is changing while applying Bloom filter and without applying Bloom filter. That way you'll be getting better intuition out of it. Along with that, I'll be providing some more documentation link in the description box where you can explore about this Bloom filter indexing in detailed manner. So this is all for this video. If you find this video helpful, then please like, share and comment. Subscribe our channel if you have not subscribed till now, and don't forget to press the bell icon to get the notification of our latest videos. Thank you for watching.